In this lesson, which will take place over different videos, we are going to look at calculations involving Ka and Kb. Before we do some examples, there are several things to note. One, of course, don't include water in your equilibrium constant expressions because equilibrium constant expressions do not include liquids or solids. The units for Ka and Kb are moles per liter, so we will include those. And Ka times Kb is equal to Kw. The first type of Ka-Kb calculations we will look at are those when equilibrium concentration of one species is given. Example 1. Calculate the Ka of a 0.75 molar solution of nitrous acid that has an equilibrium hydronium ion concentration of 0.36 moles per liter. You will notice that this type of question is very similar to those in the equilibrium unit. The only thing with these types of questions is that we are being specific to acids or bases. This example is asking us to calculate something about nitrous acid. You will notice that they did not give us the formula for nitrous acid. If you do not remember what nitrous acid is, it's okay. Go to your acids and bases strengths table and find nitrous acid in the list. The formula is next to it, and it is HNO2. Okay? We also know that nitrous acid is not one of the 6 strong acids. And in the event we do not have one of the 6 strong acids, then we are going to react this with water since it is an aqueous solution. It is not just going to break apart into its component ions because it does not dissociate or ionize 100%. You'll also notice in the acids and bases strengths table that nitrous acid is above water. Therefore, it will act as the acid while water will act as the base. We'll also notice that HNO2 or water is not strong, so this in fact should be an equilibrium arrow. Therefore, the products are going to be NO2 negative and H3O positive, or hydronium. Seeing as we made hydronium and not hydroxide, this further shows that we are talking about an acid, which is why we were asked to calculate the Ka and not the Kb. Again, since this is a weak acid and not a strong acid, we cannot use stoichiometry, so we have to go back to our ice table from the equilibrium unit. Remember that water is a liquid, which is not included in our equilibrium expression, so we're not going to do anything about it in our ice table either. The initial concentration of HNO2 was 0.75. We always have no reactants to initially start. We lose reactants and gain products. Notice that all of the coefficients here are 1, so we have 1x each. And our equilibrium line is a combination of the first two. Once you have your ice table set up, this is when you go back to the question for the extra piece of information. And the extra piece of information here was that the equilibrium hydronium ion concentration, so the hydronium ion concentration at equilibrium was 0.36 moles per liter. At this point, you ask yourself, according to you and your ice table, what was the equilibrium concentration of the hydronium ion? Well, we find the hydronium ion, and we go down to the equilibrium line, and we notice that we called it X. Therefore, we know that X is equal to 0.36. Once you know what X is equal to, you can then find the equilibrium concentrations of the other species required to calculate Ka. NO2 at equilibrium is equal to X, so this is also 0.36 molar. And HNO2 at equilibrium is 0.75 minus X to give us 0.39 molar. Once you have all of the equilibrium concentrations, you can now answer the question by solving for Ka. Of course, write out what your Ka expression would look like first, which is products over reactants raised to the power of their coefficients, not including liquids and solids, so water will not be included here. So we have 0.36 molar times 0.36 molar all over 0.39 molar. Two of these molars will cancel out to give us the units moles per liter as suspected, and this is 0.33 moles per liter for the Ka value. Example 2. A 0.35 molar sodium hydrogen carbonate solution has an equilibrium concentration of carbonic acid of 0.11 molar. Calculate the Kb for the base. Well, the first thing we need to do is write out the formula for sodium hydrogen carbonate. This will require a review of Science 1206, where you look up the sodium ion, Na positive, and the hydrogen carbonate ion, which is on the back of the periodic table, which is HCO3 negative, and do the crisscross. This will give us NaHCO3, aqueous. At this point, you have to ask yourself, what type of compound is this? And you should notice, since there is a metal, sodium, and nonmetals, hydrogen, carbon, and oxygen, that this is an ionic compound. And what do ionic compounds do in solution? They dissociate. So there is actually Na positive present and HCO3 negative present. This should also remind you of writing out the Bronsted-Lowry acid-base reactions where metals are not included. So since metals are not included, we are not going to include the fact that sodium is present. Therefore, instead of using sodium hydrogen carbonate, we're actually going to use just the carbonate ion. Is the carbonate ion a strong acid? No, it's not. Therefore, we need to react this with water, and we're going to use equilibrium arrows here. Normally, one would predict that the hydrogen carbonate ion would act as the acid while water would act as the base. However, pay close attention to how this question is worded. You are being told that at equilibrium we have a certain concentration of carbonic acid, which means we need to make carbonic acid in this equation. In order to make carbonic acid, which is H2CO3, the hydrogen carbonate ion must accept another proton. So it is in fact acting as the base to produce H2CO3 and OH-. Another clue that this is in fact written correctly is that we have produced OH- and the question asked us to calculate the Kb for the base. And producing OH- is a hint that we do in fact have a base. We must now write out our ice table, keeping in mind that water is not included in the Kb value, so we don't need to worry about it here. The initial concentration of the sodium hydrogen carbonate was 0.35 molar, and notice that the sodium hydrogen carbonate and the hydrogen carbonate ion have a one-to-one relationship. Therefore, it is also 0.35 molar. And we start off with no products. We lose reactants, we gain products. Notice that the coefficients here are all 1 again. You'll notice that in this unit. And the equilibrium line are the first two put together. Do note that in these types of questions, instead of maintaining the variable in the ice table, you can take the numbers and plug them back into the ice table. You won't see me doing this in the instructions, however, it is perfectly acceptable. We now go back to the question for the extra piece of information, which was about this carbonic acid at equilibrium. And we were told that the carbonic acid solution, H2CO3, at equilibrium is 0.11 moles per liter. At this point, you ask yourself, according to you and your ICE table, what did you say the equilibrium concentration of carbonic acid was? We find carbonic acid, we go down to the equilibrium line, and we find that it is in fact X. So therefore, we have solved for X yet again. Once you have solved for X, you can solve for the other species required to find the equilibrium expression. And hydroxide at equilibrium is X, which is 0.11 molar. And the hydrogen carbonate ion at equilibrium is 0.35 minus X, which would be 0.24 molar. I'm actually going to write that down below to give myself some room. So this is 0.24 molar. We can now write our Kb expression, products over reactants raised to the power of their coefficients, not including water, of course. And we can plug in the equilibrium concentrations that we have found, as that's the only thing that you can plug into an equilibrium expression. We have 0.11 molar times 0.11 molar, all divided by 0.24 molar. One of these molars cancels with the other to leave us with a final answer to the appropriate number of significant figures of 0.050 moles per liter.